Now that we have a new integration trick in our bag of tricks, we can solve a lot more application type problems that we wouldn't be able to solve before, or that we had to sort of trust other formulas for before, right? But now we can work it out for ourselves. So as a couple examples, let's start with this one. Let's find the volume swept out by the region bounded by the graph of sine and the x-axis for x values from 0 to pi when we rotate this about the y-axis. So just to get a handle on what that's going to look like, so from 0 to pi, that's just sort of the first bump on the graph of sine. And we're going to rotate this around the y-axis like this. So we get this sort of, I don't know what to call this. It's kind of like a, I don't know what to call this thing. It's got this weird divot in the middle. It's sort of roughly donut shaped, but the donut kind of pinches closed in the middle there. So to find the volume here, for this region, clearly we want to be slicing this region vertically. If we tried to slice this region horizontally, coming up with good expressions for these, the position at the end of this red line segment would be pretty tricky. It'd be a mess. So let's not do that. Instead, let's slice this thing vertically, as I suggested here. But when we rotate this slice, right, we get cylindrical shells. So we're going to be doing shells here. So the volume is the integral of, so the circumference around the shell, so that's 2 pi times the radius of the shell, times the height of the shell, dx. Our bounds are going to be from 0 to pi. So integral from 0 to pi of 2 pi times the radius of this shell. And the radius of this shell is this red distance, but that's just x. So the radius is x, and the height of this shell is the graph. So it's the top minus the bottom, so sine of x minus 0, that's sine of x dx. And you can see this sort of integral, this is a prime case of using integration by parts. Right? We can move this 2 pi outside the integral, but a polynomial times a sine or cosine, that's prime integration by parts territory. So let's let u be x, and dv will be sine of x dx. That means du is dx, and v itself is negative cosine x. Don't forget that minus sign. So now we can use our integration by parts formula. So u times v, so minus x cosine x. And remember, this is a definite integral, so we need to evaluate from 0 to pi, minus the integral from 0 to pi, of v times du, so minus cosine x times du is just dx. Okay. Let's simplify these minus signs here. These turn into pluses. So minus, now evaluate at our bounds, pi times cosine of pi, minus, and then plug in 0, 0 times cosine of 0, plus, now we do this integral of cosine is sine of x from 0 to pi. So we get minus pi cosine pi. Cosine pi is minus 1. And then minus this part here is 0. So I'll stop writing that part. Plus sine of pi and sine of 0 are both 0. So this last sine term just gives us 0. And so finally we get pi. So the volume of this this rotated thing is exactly pi cubic units. So a bit of a surprise. And right, this integral is one that we would not have been able to do before we had integration by parts available to us. Let's look at another example. Let's find the centroid of this region. It's bounded by x equals 0 right here, x equals 2, y equals 0, the x-axis, and the graph of y equals e to the x. So to find the centroid, right, we need to find the mass, the moment about the y-axis, and the moment about the x-axis. So 3 different integrals to do. For the mass, right, so remember for centroid, if your density is constant, the centroid is the same as the center of mass. So we'll use our usual tricks for getting the moment about the axes and the mass, but we'll just take the density to be 1. Right? As long as your density is constant, the density will cancel when you actually find the coordinates of the centroid. So we might as well take it to be 1 because the density is going to cancel anyway. Okay, so the mass is the integral of the density, which is 1, so I'm not even going to write it, times, so we need to, I guess we're really just finding the area of this region. So e to the x minus 0, right, the bottom of this region is at y equals 0, dx. And this is from 0 to 2. So this integral is e to the x from 0 to 2, and that's e squared minus 1. All right, now how about moment about the x-axis? Moment about the x-axis, that was the integral of the density, which we're taking to be 1, over 2 times the top curve, e to the x, squared, minus the bottom curve, which is 0, squared, dx. I think I'm remembering this formula right. So 1/2 integral from 0 to 2 of e to the 2x dx. So 1/2 times, antiderivative for e to the 2x is 1/2 e to the 2x from 0 to 2. So we get, let's see, 1 over 4 times e squared, no, e to the 4th minus 1. Okay, and now moment about the y-axis. Moment about the y-axis is integral from 0 to 2, the density, which again is 1, so I'm not going to write it, times x times the top curve minus the bottom curve, which is just e to the x. And here you see prime example of using integration by parts. So we'll let u be x, du is dx, dv is e to the x dx, v is e to the x. So we get u times v, so x e to the x from 0 to 2 minus the integral of e to the x dx from 0 to 2. Okay, this first piece gives us 2 times e squared. And then when you plug in 0, you get 0 because of the x there. So minus 0 here. Minus, and then integral of e to the x is e to the x from 0 to 2. So 2e squared minus e squared minus 1. So e squared plus 1. And that's the moment about the y-axis. Okay, so now we have all the pieces we need. The mass was e squared minus 1. Moment about the x-axis was, I don't remember, 1/4 e to the 4th minus 1. And moment about the y-axis is e squared plus 1. So the centroid, x bar, y bar, is going to be, remember it's the moment about the y-axis divided by the mass, comma, moment about the x-axis divided by the mass. So e squared plus 1 over e squared minus 1, comma, e to the 4th plus 1 over 4 times e squared minus 1. And there we go. So maybe we should get decimal approximations for this just to see where it ends up lying on the region, because you know, our eyes are sort of good at estimating centroids. So let's just see what we get. So e squared plus 1 divided by e squared minus 1. So for the x coordinate, I get 1.31 about. I mean, of course, there are many more digits there. And then for the y coordinate, so e to the 4th plus 1 divided by 4 times e squared minus 1. Close that parenthesis. Close that parenthesis. Okay, I got 2.175, so 2.18. So 1.3 and 2.1. 1.3 about here, and 2.1 about there. So there's the centroid of this region. So if you cut this region out of cardboard, it would balance if you put it on the tip of a pin on that spot. And that looks about right? There's this big lump of stuff below the centroid, but that's all close to the centroid. Remember, the way that moment works is stuff farther from the center sort of counts as more since it has a longer lever arm. So this big chunk of stuff close to the centroid is balanced out by this long thin piece that reaches far away from the centroid.